Okay, so let's start. Just reminding you that there's going to be an exam on the 17th. Next Monday, instead of a lecture, we're going to do a poster session just outside here, same time. So, and you saw on Piazza some instructions for what to do. Questions? Okay, so homework 5 is going to be out tonight. It's going to be much shorter than all the others. Basically, it's sort of some versions of an exam. So should take just a couple of hours, plus one other question. So altogether, just a few hours. Hopefully will help you prepare for the exam. Okay, so let's see where are we. So unless there are any questions. Okay, so we talked about Bayesian learning. Naive Bayes was the key example. Talked about EM. And we want to generalize it a little bit to talk about probability distribution in more general. And think about what does it mean to learn probability distribution. So the context is you can think about what we are doing here as unsupervised learning. We talked about it a little bit last time because we're just going to see data. There's not going to be a notion of a label. Data and then learn a representation of the data so that you can say something about it, or you can say something about the probability of other events relative to this data. So I gave the example of naive Bayes. In naive Bayes, which is this picture, we thought about the y as a label and all the xi's as the features. You don't necessarily have to think about the y as a label. You can just think about it as I have n+1 variables, and I see data, and I want to be able to estimate it. And this picture, the important thing to understand here is that by drawing the n+1 variables this way, with a y that has no parent, and xi's that have a single parent, an edge going toward them from y, we actually encode. It's a convention. We encode a conditional probability independence assumption. And the specific assumption is the one that is written there, that xi and xj are independent given the parent y. And you know about this already in naive Bayes. What we're going to do is we're going to generalize it to general probability distribution. What does it give us that we make this assumption? What it gave us is that we could easily compute this joint probability distribution. P of y, x1, x2 up to xn, P of n+1 variables. We could decompose it in this simple form on the right, which basically means that instead of having 2 to the n+1 variables to represent this joint probability distribution, all we have is a number that is linear in n. Yeah.
This is notation, but are there n variables or n+1?
There are n+1. You see, x, y, x1, x2, altogether n+1. So I'm calling, I just left y there so that you'll see that it's the same naive Bayes that we played with earlier, but I can call the variables any names I want, right? So there are n+1 variables, and therefore there are 2 to the n+1 instantiations of these n+1 variables, and each one of them I can assign a probability. They all have to sum to 1, so it's just 2 to the n+1 minus 1 numbers. And because of the assumption, we don't need so many parameters. We can write it in this way. And that's exactly what we want to generalize today. Now, another comment that we made at the end last time is that because we know the joint, any event that you want to compute the probability for, and this is an example of an event, the event where x1 is 0, x2 is 0, and y is 1, I can compute the probability for it. The generic way to do it would be to marginalize, which is going to be a long sum over all variables I don't know the values of. But because of the assumption, I can write it in a much simpler way, this way. Okay, so this is all things that you know, and we talked about at the end of last time. And today we want to generalize it to general probability distribution. Now, when we talk about general probability distribution, it's just a function, right? It's a function from assignments to a number between 0 and 1, a function that has to satisfy some properties. Specifically, it's a positive function, and it, over all the instances, it has to sum to 1. So there are many ways to represent functions like this, and we are going to care about one important representation, which is called Bayesian networks. So what is a Bayesian network? It's basically a directed acyclic graph. Looks like this. And again, just like in the naive Bayes thing, the graph itself, it's a convention. The graph itself encodes conditional probability assumptions. What are the conditional probability assumptions? It's the assumption that for all variable x, x is independent of its non-descendants given its parents. So in this case, I have, for example, the variable x. X has parents z3, z2, z1. And I can say that x is independent of x2 given these parents. And in general, because of this independence assumption, I can decompose the joint probability distribution here too. Again, n+1 variables is what I've written here. I can decompose it to the product of p of xi given the parents of xi. This is a special case, p of y. Y does not have parents, so it's just p of y. And the important thing for you to realize, this is really a theorem. It's a theorem that comes up from writing the joint probability distribution using the standard product rules of probability distribution and this assumption. So you can take this and just write it yourself, and that's what we have. So that's really the important thing to know, and we're going to go through several examples, so this will become clear. Okay, so a Bayes net, just as in the picture that we've seen, it's a collection of random variables that are the nodes. Edges, you can think about, represent causal influences, but really what we care about is we care about for each node the set of all parents, because this determines the joint probability distribution. A variable with all its parents is called the conditional probability table, CPTs, and that's what we care about. So you can think about Bayes net as a way to represent a set of conditional independence assumptions on the variables, or you can think about it as a data structure that together represents a joint probability distribution. And the important thing is that it's a compact representation of the probability distribution. So let's take an example and convince ourselves that we understand what's happening here. So here's a story. I'm going to use this story and build the graphical representation, the Bayes net representation that corresponds to this story. So here's the story. A burglar alarm in your house rings when there is a burglary or an earthquake. And earthquakes will be reported on the radio. If an alarm rings and your neighbors hear it, they will call you. So now I'm going to take this story, model it as a probability distribution. So I'm going to invent a few random variables. These are the random variables. So I have a random, all of them are going to be Boolean variables. Earthquake, yes or no. Burglary, yes or no. Alarm, radio. My neighbor Marie called. My neighbor John called. These are the variables. And now I want to make a graphical model out of it. So I'm going to make some independence assumptions. And the way I'm going to do it is I'm going to read the story and add corresponding edges. So if there is an earthquake, you'll probably hear about it on the radio. An alarm can ring because of a burglary or because of an earthquake. So I'm going to add these edges. Okay? Now, by adding these edges, I made assumptions. For example, I made the assumption that whether John calls, Boolean variable, yes or no, is independent of whether there's an earthquake, given that there was an alarm. Because alarm is the parent of John, and once I know the value of alarm, I don't care about what happens above it to determine the probability of whether John calls or not. Okay, so that's the assumption here. These are the set of assumptions that we have. And once I have this set of assumptions, I can answer some questions. Here are two of the questions that I want to ask. Yes?
So is here like, I don't know if I'm ready for it, but it seems like then a big assumption here is if you hear the radio, you won't get a call.
Why?
Or is it parallel, because it's parallel to alarm, it means that both will happen and then either Mary or John will call.
So if I hear the radio, there's nothing I can tell you about any of the other variables.
But it says like the alarm will sound as well, right? If there's an earthquake?
If there's an earthquake, I know that the radio, there is some conditional probability of radio being on or off given earthquake. There is some conditional probability of the alarm being on or off given earthquake. What I do know is that alarm and radio are independent given earthquake. Right? That's the assumption I made. This is how I drew it. So if I know whether there was earthquake or not, whether the alarm is on or off is independent of whether the radio is on or off. That's what this picture tells you. You don't like this assumption, you can add another edge. But that's the assumption that I encoded in this graph, okay? So first of all, why do I make these assumptions, right? So these two questions will help us, hopefully. So maybe we'll start with the second questions. Let's say I make no assumptions. No assumption means that I have a complete graph, right? A click. Everything is dependent on everything else. No independence assumptions whatever. How many parameters will I need to represent the probability distribution over these 6 variables? Boolean variables, 6 Boolean variables. How many assignments are there given that I have 6 Boolean variables? 2 to the 6. Each one of them could have some probability. Now I'll get a probability distribution, right? But not exactly, because all these probabilities have to sum to 1. So really 2 to the 6 minus 1, 3 parameters. Okay? That's what I have. So it's 63, right? A large number. So that's the answer to the second question. Now, how many parameters do we have here? So let's see exactly what parameters do we need here. So let's add the parameters. So this is the same network. Now, what do I need? I have 2 nodes that have no parents over there, earthquake and burglary. So I need to know the probability of burglary. Now, remember, when I write P of B, that actually encodes 2 numbers, P of B being on and P of B being off, right? We write this compactly this way. Same thing for P of E. Now I go down, radio. Radio only depends, well, it depends on many things, but it's sufficient for me to know the conditional probability of radio given earthquake. This does not mean that radio is independent of whether John calls. In fact, it depends on whether John calls, indirectly through the other variables. But what I need to know in order to compute the joint is P of radio given earthquake. How many numbers are in P of radio given earthquake? So radio can take two values, on or off. Earthquake can take two values, on or off. So there are really four numbers there, right? But they are not independent. Why? Let's assume that earthquake is on. Given that earthquake is on, the probability of radio being off plus the probability that radio is on has to be 1, right? So in pairs, really what I have is two independent numbers there. Okay, everyone agrees with that? Now let's move to alarm. Again, alarm could depend on many things, but in order to write down the joint probability distribution, all I need to know is the conditional probability of alarm given burglary and earthquake. How many numbers? 8 numbers, right? So A, E, and B, each one of them can be on and off, so it's 8 numbers, but again, they are not independent. So for a given configuration of E and B, let's say 0, 0, A can be 0 or 1, but these two numbers have to sum to 1. So given every configuration of E and B, I have two numbers that have to sum to 1, so really just 4 independent parameters. And so on, we can continue this way. Even if I don't account for independence, and let's do simple counting. So what I have is 2, 2 at the top, 4 here, 4 here, 4 here, and 8 here. So this is 12, 20, 24 numbers instead of 63. So I made assumptions, and I cut down significantly on the number of parameters I need to know in order to represent the joint probability distribution. Questions? Yeah. P of E can be 0. E can be 0 or 1. There could be an earthquake or not an earthquake. So I need to know the probability that there is an earthquake, and 1 minus it is the probability that there's no earthquake. Yes. So I said, in each one of these boxes, I can either count all the numbers, or I can count the number of independent parameters. So if I want to count independent parameters, then I would count 1 at the top here, and 1 at the top here, and 2 here instead of 4, and so on. So what I did, just as a shortcut, I counted all the parameters without accounting for independence. Okay, and I got 24. If you want to account for independence, you'll get about half. But is it clear what we're doing here, what we're counting? Okay. Okay, so now I have everything. Now I can compute the joint probability distribution. And here it is. So what is the joint probability distribution? It's a probability distribution over E, B, A, R, M, J. Notice that what I'm encoding there is 64 numbers, right? Because E, B, A, R, M, J could take 64 different instantiations. All I'm telling you is that in order to compute any given instantiations, the probability of E being 0, B being 1, alarm is off, radio is on, M is off, John did not call. Given assignment here is how I'm going to compute it. And what I did here is basically use the product rule. So P of all this is, I can write always as P of E given this given E. Okay? And so I copied P of E here, and then I continue. This one I can write as P of B given the rest, given E and B. And I can continue this way and decompose this until that's what I get. So basically what I've done here is I proved to you, in this specific case, that the composition that I argued before is a theorem. But I did it just for this specific case. So what we have here is the joint probability distribution is the product of the probability of each variable given its parents. Okay, so now that we understand Bayesian net, what are the computational problems that we have? There are really two computational problems. One of them is learning, and you can learn the structure of the network, which I gave you here, and you can learn the parameters. That is, you see that there is an arrow from E to R, you know that you need to learn P of R given E. So in fact, learning the parameters is the easy thing because you see a lot of data. You know that you have to learn P of R given E, depending on what assumption you're making on this edge. Do you assume Bernoulli? Do you assume exponential? Do you assume Gaussian? You're going to compute the MLE, the most likely estimate of P of R given E. So this is the easy part. The structure is the hard part. How would we compute the structure? What would be the idea? What would be the guiding principle? There's one answer to all the questions in these 2 weeks of the semester. Yes?
So the conditional probabilities, so how different variables depend on other variables?
True, but if you were to say one phrase, which is the answer, what would be the guiding principle?
Just whether two variables are independent or not.
I told you that, right? So by drawing it this way, okay, I see what you're saying. So yes, you want to know whether two variables are independent or not, but how would you determine that? I'm going to give you data. Right? So learning the structure basically means I want to know whether there is an edge between burglary and alarm. How do you figure it out? So you're on the right track. But what would guide you in deciding whether to put an edge there or not? So the single answer I'm looking for here is maximum likelihood. So I give you data. And what you want to ask is, which structure is the most likely structure given the data? So here is one structure. If I give you this structure and I give you data, you should be able to compute, just using this formula here at the bottom, what is the probability for each data point that I gave you. And therefore, what is the probability of all the data that I've given you? I'm assuming that data items are always independent, so it's just the product. So if I give you one network, you can compute the probability of the data given the network. Now I can change this network. Let's say I'm going to add an edge here from Marie called to John called. That means that it's a different Bayesian net. The joint is going to be written differently, and now you can compute the probability of the data given the new network. Let's see which one is more likely. So basically, that's the principle. It's not easy in general, but we're going to show it in a very specific case of a simpler network. So that's one computational problem, how to learn the network. The second one is inference or reasoning. So really, there are two inference problems. One of them is, given an event, what's the probability of the event? What does it mean when I say an event? I can take this network and I can instantiate it. I want to know what's the probability of M and J being 1 given that B is 0. I can compute it, right? Because I know how to compute the joint, so I know how to compute any event that I want. So that's inference problem number one, computing the probability of an event. The way I've written it here is, I want to know what's the probability that the radio is off, the alarm is off, given that earthquake is something. So that's one problem. The second one is most likely explanation, which is, I want to know let's assume that E, earthquake, is on. I want to know what is the most likely value of a specific set of variables. For example, what's going to be the most likely assignment of radio and alarm? Will both of them be on, both of them be off, one off, one on? Tell me which one is the most likely assignment. So you can think about it as trying, basically it's an argmax problem, try all values of this y. In this case, as I said, y is radio and alarm. There are 4 options, and compute the probability and tell me which one is the maximum. So this is a very important computational problem. Now, both of these computational problems are difficult computationally. The first one much harder than the other. But there are algorithms, there are approximation algorithms, and also good exact algorithms that often work well in practice. But we are not going to talk about it. That's a little bit too much. Instead, we're going to simplify the network. I'm going to restrict everything I'm going to say from now on until the end of today to simpler Bayes nets. There are going to be only trees. So we're going to talk about tree-dependent distributions. Unlike the previous one, there could be cycles. Trees have no cycles. Every variable has a single parent. So still, I can write a joint this way. It's exactly the same as before, only that each variable xi has only one parent or no parents. Okay? So the independence assumption, again, is the same, only that I can write it in a simpler way. Every variable x is independent of other nodes given its parent. Okay, so that's a simpler probability distribution. And we only need to know 2 numbers for each link. Everyone agrees with that? 2 numbers for each edge? Yes, no? Okay, convince yourself. And then, what is the inference problem? So, given a tree with all the associated probabilities that I drew there, I want to be able to compute the probability of an event. And there are different kinds of events, and I'm going to give a few examples and convince you that we know how to do this. So let's assume the event I care about is what's the probability in this tree that P of x is 1. Now notice, I don't know, it's not written there. What is P of x? What do I know? I know P of x given z, right? That's what's given to me. And I also know other things. How do I get from these conditional probabilities that are given there to P of x? So let's write it down. So I'm going to basically use basic probability formulas. P of x being 1 is, I'm going to climb up the tree and use this total probability formula. So P of x being 1 can be written as P of x being 1 given that z is 1 times P of z being 1 plus P of x being 1 given that x is 0 times given that z is 0 times P of z being 0. You should agree with that. Now, still not helpful. I know P of x given z, but I don't know P of z. So I continue to climb up the tree. P of z being 1, I'm doing in exactly the same way, climbing up one from z to y. P of z being 1 is P of z being 1 given that y is 1 times P of y being 1 plus given that y is 0 times P of y being 0. Now, I know P of y because y has no parent, so I know P of y. And I know P of z being given y, so now I know everything. So now I can compute, with 2 steps, I computed P of x. Question?
Do you then you also need to figure out the probability z equals 0? And then...
Yeah, of course. Same thing, yeah.
Would you multiply then each line? Like the top line of that one times the line below it?
No, I would put an equal here, and I know already P of X given Z, both this one and this one. I have values for this. It's written in my conditional probability table for the tree, and I just need to figure out what is P of Z being 1 and P of Z being 0. Okay. And I get it from here. Now, I wrote here only the case of P Z being 1, but exactly the same thing will give you P of Z being 0. Okay? So basically what I showed is that I can take a node in the tree and compute the probability of it. So that's one type of event. It's not the only type. So here I'm writing the P of Z being 0, but it's exactly the same thing. And now I have everything in terms of the CPTs, the conditional probability table, so I can compute the probability. Let's take another event. The important thing is, of course, that it's a linear time algorithm. All I need to do is climb up the tree. Let's take another event. Let's assume I care about the event P of X being 1 and Y being 0. So X is here at the bottom, Y is there at the top. I'm going to do the same thing. I'm going to write it. I'm going to climb up the tree until I reach an expression that makes use of the conditional probability table. So let's try this. So P of X being 1 and Y being 0 is P of X given Y times P of Y. That's always true. And then recursively, I'm going to go up the tree. So I always have a path from X to Y. It's a tree. So I'm going to climb up this path. And I know that along this path, all the conditional probabilities are known. So everything is going to be OK. So how do I do this? I'm climbing up this way. So P of X, I need to know this conditional probability, right? P of X given Y. I don't have it because there's no one edge. There's no single edge from X to Y. But there's a path. So I'm climbing up this path. So I have a single variable in the path. So I'm marginalizing over it. So it's the sum over Z being 0 or 1, P of X given Y and Z, times P of Z being given Y. Always true. Now, I'm copying it. P of X given Y and Z. What is P of X given Y and Z? It's a base net. What do I know? I know that given Z, X is independent of Y. So I'm dropping Y. All right, so instead of writing P of X given Y and Z here, I can write P of X given Z. Okay? That's the assumption. The first equality was always true. The second one is true because it's a Bayesian tree. And therefore, given Z, X is independent of Y. I just dropped Y from here. Okay? And then I copied P of Z given Y because I know P of Z given Y. There is a direct edge from Y to Z, so I know P of Z given Y. It's one of the conditional probability tables. And basically, I'm done. So now we have, again, everything in terms of the CPTs. So in the next two slides, I'm giving two more examples, P of X and U. The difference between this one and the previous one is that X and U do not have an edge between them and do not have a path, but because it's a tree, I can climb up from both of them and I will always reach the root of the tree. And that's what this is going to do. So you can check and convince yourself that you can do it. And here is yet another event. And basically, I exhausted the types of events that you can care about and convince you, hopefully, that by example, that for every event that you care about of variables in this Bayesian tree, you can compute the probability of the event. Now, there are more efficient algorithms, but my goal here wasn't to give you a systematic algorithm, but rather to convince you that it's all basic probability, and you can basically do it. So, okay, so we are done with the inference problem. Now, everything was simple here because it's a tree. If it was a DAG, there will be multiple ways to get from one variable to the root or to other variables. And this makes this problem a lot more computationally intensive, so we don't care about it. The next few slides here, in fact, talk about inference, but we are going to skip it, and I will not assume that you know inference. We are only going to stick with the trees and talk about learning tree-dependent distributions. So the first thing I want to talk about is what does it mean to learn a tree-dependent distribution? So I'm going to get data, tuples of n variables, and I'm assuming that they come from this distribution, from a tree-dependent distribution. So the first thing you have to understand is what does that mean, right? So think about the generative story, right? So someone has this tree, and they generated data according to this tree. It's the same story as in the naive Bayes, only that it's not as shallow as naive Bayes. That means that first of all, I'm going to sample the root variable y according to the probability P of y. P of y being 1 is 0.3, so with probability 0.3, I'm going to get y equal 1. With probability 0.7, I'm going to get y equals 0. I have y. Now I'm sampling w, u, z, and s according to the conditional probabilities given here. And once I have these values, I can sample v given P of v given u. I can sample t given P of t given z, and so on. So that's what it means to sample data. Now, someone gave me data, but they told me it's coming from this tree. Learn the tree. Right? Exactly the same problem that we had a couple of months ago. Someone gave us data, told us, well, it's coming from some function. It's consistent with some function, learn the function, right? So conceptually, it's the same thing, only that now, when they tell us find the tree distribution, what does it mean to us? There could be many distributions that have generated this sample of 100 examples. So again, the game we're playing here, we want to find, here's data, we want to find the most likely tree that could have generated it. So think about a coin. We are completely generalizing the coin problem that we had before. You see 10 tosses, I don't know, 6 heads and 4 tails. There could be many coins that would have generated this sequence, right? There could be a coin that is a fair coin that generated this. There could be a coin that has probability of 8.7 that could have generated this. But there is a well-defined notion that we care about here, which is the most likely coin that has generated this, right? So that's what we're after here, only that instead of one coin, we are talking about a sample, and it comes from a tree, so we want to find the most likely tree that has generated the data. Okay, it's really the same thing, only the exercise is a little bit harder because there's many trees, and we have to understand what does it mean to search in the space of trees. Okay, so that's what we're doing. We're going to compute P of t given the data, which Bayes' rule tells us it's P of d given t times P of t divided by P of d. And in fact, eventually we're going to move to maximum likelihood. So we don't care about, we will not have a prior assumption over the set of trees, but that's the problem, right? So find the tree representation of the distribution. So as I said, we are assuming uniform prior, so we don't care about the probability of t, so we really need to maximize P of d given t. So that's what we're going to do. Find TML, which is the argmax over all t's of this probability distribution. now you can already see why did I talk about inference before? Because when we evaluate the likelihood of the tree, we should be able to compute the probability of a given assignment, right? Which is the inference problem. Okay, so now that we have this, how do we compute? Continue. So first of all, we know how to decompose it as a function of the conditional probability tables. And I, again, want to remind you, we did exactly this for naive Bayes, right? So we always computed, or what you did also in the homework, you computed the most likely tree, only that it was a shallow tree, given the data that you've seen. And the way you've done it is you basically multiplied these conditional probabilities and did argmax. Okay, so let's take an example now. So what does it mean to learn probability distribution, really? Here is a probability distribution over 4 variables. I gave you the whole probability distribution, right? 4 variables means 16 instances, and I gave you a number for each one of them. In order to convince yourself that that's a probability distribution, all you need to know is, all you need to check is that all these red numbers, so what I have here is, in black, I have the instance, 0, 0, 0, 0, 0, 0, 0, 1, and so on. And in red, I have the weight of this, the probability of this instance. So these red numbers should sum to 1. Hopefully they do. Now it's a probability distribution, okay? Here's another probability distribution over 4 variables. Well, not quite, because I didn't give you the conditional probability tables, but you can see that I can continue from here and define another probability distribution over 4 variables. Okay? Now I give you the conditional probabilities. Soon I'll put numbers there. And I define probability distribution 2. Here is probability distribution 3. So notice that the conditional probabilities tables here are different. Potentially a different probability distribution. But is it really a different probability distribution? So that's a question that I can ask you. I mean, maybe all these 3 are the same distribution, only that I'm writing them in a different way. What does it mean to be the same probability distribution? So a probability distribution is a function. It assigns a number between 0 and 1 to each one of the 16 instances, and these numbers have to sum to 1. So for probability distribution 1 and 3 to be the same, 3 has to assign to the instance 1, 1, 1, 1, the probability 0.05, and to 1, 0, 1, 0, the probability 0, and so on. Each one of the instances has to be assigned the same number, same probability, right? That it's a function. For all the arguments, the value has to be the same, right? So you've seen this before. So now we're going to ask a more concrete question. Given a sample, I want to know which one of these 3 probability distributions generated it. And now we should complain, and you should tell me, well, we will never know. What you need to ask is which of these 3 is more likely to have generated it, right? Again, go to the coin example. When I show you a sequence, you don't know which coin generated it and what was the bias of the coin, but you can tell me it's more likely to have come from a fair coin than from another coin. Same thing here. So let's do it. So here's the data, 3 data points. 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0. And I'm going to compute which of these 3 probability distribution is more likely to have generated this data. Okay, let's start with this one. It's simpler. What do you think? What's the probability? What's the likelihood of this data given that it was generated by this probability distribution? Why?
It's probability of 1, 0, 1, 1, 0.
Excellent. So you just picked one point 1, 0, and 1, the first one there in the yellow rectangle, that has 0 support under this probability distribution. So this data was not generated by this probability distribution. No chance. Really, I want to take a couple more steps to do it. I'm going to use Bayes' rule, and then I'm going to say, oh, the likelihood of the tree is I'm eliminating the denominator from here, so it's sufficient for me to compute the probability of the data given the tree. I'm assuming that the data points are independent, so it's the probability of data point 1 given the tree, data point 2 given the tree, data point 3 given the tree, the product of these. And because the first one, as you identified, is 0, the product is 0, this probability distribution did not generate this data. Yes?
Why do you also eliminate the prior?
Because I said 2 slides ago that I'm going to assume that I have uniform priors over all the trees, and I'm moving from maximum posteriori to maximum likelihood. Okay, so I'm eliminating P of t. All of them are 1 over the number of trees. Okay, so the probability of this data given this table is 0. Now we can move to probability distribution 2. And here, a little bit more computation. I'm going to give you the numbers, right? So what are the numbers that define the tree? And this is important because this will verify that you understand what I'm talking about, right? So you have to know what are the numbers that I really need to define this tree. So I need P of x given 4, it's at the root here, which is 2 numbers, but I need one of them because the second one is 1 minus. I need x1 given x4. So I need to know x1 being 1 given that x4 is 0. And this already gives me x1 being 0, given that x4 is 0. But I also need what's the probability of x1 given that x4 is 1. Okay, so 2 numbers here, 2 numbers here, 2 numbers here. And now I can compute it. So what's the likelihood of the tree given that this is the data? I'm computing it for 1, 0, 1, 1 given the tree. So what is 1, 0, 1, 1? X4 is 1. You can see this. X1 given X4, both are 1. X2 being 0 given that X4 is 1. X3 being 1 given that X3 is 1. So it's the product of these conditional probabilities. And then I'm substituting here. Let's look at this number here, the next to last, 2/3. These 2/3 come from X2 being 0 given that X4 is 1. Now it's not written here. Because given that X4 is 1, I've given you X2 being 1 given that X4 is 1. But X2 being 0 given that X4 is 1 is just 1 minus it. Okay? So you see that while there are, in principle, 4 numbers here, 4 numbers here, 4 numbers here, really I need 2 of them. So I need 6 plus 1 number at the top. 7 numbers determine everything, and I showed how to compute the probability of one of the instances. Questions? Okay, we can do this for the others, and hopefully if I didn't get it wrong, that's the number that we get. And then we can do the same thing for distribution 3. And again, I'm defining the distribution. Again, all I need is 7 numbers. Different numbers, right? Because the structure is different, so the conditional probability tables are different. So here, for example, I need P of x3 given x2, and before I didn't need P of x3 given x2. And again, I can do the computation, I get this number, and it so happened the distribution 2 has the highest number for this data set, so I conclude the distribution 2 is the most likely distribution to have produced the data. Questions? Okay, so we kind of learned how to find the most likely tree, given data. Why do I say kind of? Yes?
So do you guess the tree structure? Like you had to give 3 options.
Right. That's exactly why I said kind of, because it's unsatisfactory. So where are we now if we want to compare ourselves to what we've done before. Let's go back to the coins. So the first thing that we did in the coin games, I said, I have two options for the coin bias. It could be fair or 0.7. Let's look at data and compare which one of them is more likely, and we chose. That's what we did now with the trees. I suggested tree distribution, as you said, and showed you that I can compute the likelihood of the data given this tree distribution and choose the most likely of the three. But that's the uninteresting case, because really with the coin also, eventually we move to the case, well, how do you know that it's these two? I mean, there are infinitely many options. Let's figure out how to quickly search the set of all possible biases of the coin. And luckily for us, there is derivatives, so we could do some optimization, and we differentiated the likelihood function and found the value. Here, luckily for us, it's discrete. So we can just write down all the trees and do it. But you probably don't want to do it because there are too many trees on n variables. So we need to find a better idea. So what we're going to do in the next 15 minutes is going to see that, in fact, it's possible to efficiently search the space of all possible trees without writing down all the trees and find the most likely tree, which is really a very, very nice algorithm and the reason why we can learn Bayesian trees. So we really need a systematic way to search the family of this family of distributions. So, okay, so I want to pause for a second so we make sure that we understand what we are after. So we have data points. We are looking for a target distribution. We agree that we cannot find the target distribution. Instead, we're looking for a maximum likelihood distribution. Now, remember that everything we've done in this course, we are after generalization. You could tell me, well, I have these 3 data points. I have the data. From now on, I can use this to make predictions. But really, you cannot, right? You cannot use the 3 data points that I gave you to make predictions on other data points that you've never seen without assumptions. You cannot tell me what's the probability of x4 equals 0 or x1 and x2 being 1 just from these 3 data points. You have to make assumptions. And the assumptions that we are making now is the data comes from a probabilistic tree. The assumption that we made earlier in the semester, the data is consistent with a linear function. So we have to make this assumption to support generalization. Okay, so what's the problem? We are assuming, there are 2 versions that we can assume here. The first one, the simpler one, is we're given data. Someone told us that this data came from a tree-dependent distribution, and we want to find the most probable tree representation of this distribution. Second option, which is slightly more interesting, is given data, someone told us that it came from a probability distribution. We don't know that it's tree-dependent, could be more general. But because we are computationally challenged, what we're going to do is we're going to say, okay, we're going to find the best tree-dependent distribution that we can for this data. Because we don't know how to learn general probability distribution representations, we're going to learn it into a tree representation, and that's it. So again, try to think about the analog to what we've done earlier in the semester. We started by saying, well, we look at data, we know that it's linearly separable, and therefore there is a linear function that is going to be consistent with the data. Later on, we said, we have data, we don't know that it's linearly separable, but we're going to learn it with a linear separator. We know that we're going to make some mistakes, but that's what we know how to learn well, so we're going to learn this. So it's really analogous to this. So in pictures, here is the space of all three dependent distributions. In the first story, the target distribution is here. In the second story, we're looking at the space of all distribution, much, much larger space, and the target distribution could be here. In both cases, we are going to learn something that is inside the space of all three distribution. It could be that we're lucky and we got the right distribution that generated the data. But either way, we want to learn something that is close to it. So you can think about, that we learned which red point do we learn in this space of all three distribution. We want it to be the closest to the real one. Okay, so that's the game we're playing. And again, we are following conceptually the simple-minded algorithm that says, in principle, we want to touch all the trees, compute the likelihood of all the trees, and do argmax. Okay, so I'm going to introduce in the next 5 minutes a little bit of math. I'm going to skip most of the math, just some definitions, so that we'll understand what we're doing. We will not do the derivations. The first issue is, because of this picture, I need to have a notion of a distance between distributions, because there's the distribution that generated the data, the distribution that I'm going to learn, and I want to make sure that I know something about the distance. So the first thing we're defining is a distance between two probability distribution. It's something that is called the KL divergence. For two probability distribution, P and T, discrete probability distribution, that's the way we define the distance. It's the sum over all instances x, P of x times the log of P of x over T of x. There's no magic here. I mean, you can define your distance in many, many ways. A probability distribution is just a function over instances. So here is the set of instances. There's a function over it. Let's call it P. There could be another function over it. And you can think about many ways to compute the distance between them. For example, for each x, you can do P of x minus T of x, absolute value, sum over all the x's. That's also a distance. So there are many ways to define distance. This one is a nicely behaved function that you may have seen in other cases. So that's one thing we need to know. The other thing we need to know is, I need to decide whether I'm going to put an edge between x and y in my graph, in my tree. So I need to be able to rank dependencies and decide, yes, I want to put an edge between this x and this y, but I don't want to put an edge there. The way we're going to do it is we're going to do it with something that is called mutual information between variable x and variable y. And I'm defining it here. What is the mutual information between variable x and y? I'm going to sum over all values that x and y can take, P of xy, the joint probability of x and y, times log of P of xy divided by P of x, P of y. If you remember what's independence, what you see under the log there is the condition that you test for independence between x and y. Right? If x and y are independent, that P of xy is equal to P of x, P of y, which means that this is going to be 1, and this is going to disappear from the sum. But altogether, this mutual information is something that allows us to compute how dependent x and y are, and therefore whether I want to put the edge between them. Okay, so now that I have these two, I can come up with an algorithm. So the algorithm is given m independent measurements. For each variable, I'm going to start by computing P of x. Right? So really n numbers, P of x for each of the variables. For each pair of variables, I'm going to estimate also P of x, comma y. again, if I have n variables and features, this means n square numbers. And this is actually something that you already have to start thinking about. So we often think about computation. We don't often think about space in learning. Right? When you learn linear functions, you had n numbers that you cared about. When you did naive Bayes, you had n features, you cared about n numbers. What happens here? If you have 1,000 features, that means that how many numbers you have to keep? About 1 million. Right? If you have 1 million features, 10 to the 6, you have to have space for 10 to the 12 numbers. Too large, even in today's storage cases, right? So while the algorithm I'm going to go over now is really a beautiful algorithm, whenever you learn a probability distribution and you care about edges, your space is quadratic, and you should care about it. Maybe you cannot even do it with too many features. Even if it's quadratic, it could be very, very large. So this is something to think about, but we won't think about it now. We'll continue with the algorithm. So I computed P of X, P of XY, and now I can compute the mutual information. So for each pair of variables, I'm going to compute the mutual information. And now I have n variables. I'm drawing the complete graph, the clique, undirected graph on all the variables. I'm going to place the I of xy, the mutual information, on the edges. And now I have a complete tree, a complete graph, but I want to make it a tree. How do we take a graph and make it a tree? Most of you have seen it. I'm going to take the spanning tree of the graph. Right? So what does it mean to take a spanning tree? Maximum weighted spanning tree. So I'm going to choose the highest possible I of xy that I can. I'm giving here a quick summary of the spanning tree algorithm. It's a very intuitive, greedy algorithm. Basically, my goal is to find a subset of the edges that form a tree. How do I do it? I sort the weights. The weights are my I of xy, and I'm going to start greedily with the largest one, and then continue down this sorted list as long as I don't create a loop, because I want to end up with a tree. In case of a loop, discard this weight, move to the next one in my sorted list, and this algorithm will create a tree. Very easy to see. It's going to touch all the edges, and it's not difficult to see that this is actually what we want. It's the heaviest tree that you can get from this graph. And it's a relatively efficient algorithm, basically scales with the number of edges n squared times log n. Okay, so let's go back here. We have an algorithm. We build a tree. It's still not a Bayesian tree. To make it a Bayesian tree, I first need to make it a directed tree. So the question is, how do I take a tree and make it a directed tree? I'm suggesting here a simple algorithm. Choose any root you like, any node you like, and set the direction of all the edges away from it. That will make it a directed tree. Agreed? And then I have to make it a Bayesian tree, so I'm going to place the corresponding conditional probabilities on the tree. That's an algorithm. Now, in order to convince ourselves that this is a good algorithm, there are really three things that we have to prove. I have to prove, one, that the right thing to do is to place the conditional probabilities on the edges, because I started with mutual informations. Why don't I leave it there? Why do I have to place the conditional probabilities? Two, I have to show you that using the mutual information as a way to choose the best tree. That's what I did, right? I did spanning tree with mutual information on the edges is the right thing to do. And three is I have to show you that the way I transformed the undirected tree to a directed tree makes sense. So I'm not going to show 1 and 2. It's in the slides, but you'll have to believe. 3 is actually really simple and nice, and you will do it in the homework. You will prove, and I'll say a few more things about it, that you can take a directed tree, an undirected tree, choose any node that you want, direct everything away from it, and you're going to get the same thing. So it doesn't matter which node you choose to be the root. As long as you direct everything from it, you're going to get the same probability distribution. OK, so let me skip now over the math for 1 and 3, 1 and 2, because we don't, you're going to believe it. And we're going to get to 3 and to an example that I'll finish with. So in 3, what you're going to do in the homework that will be released tonight, transform the resulted undirected tree to a directed tree. So you're going to choose a root variable, direct it away from it, and you will show that it doesn't matter which one you choose, you will always get the same probability distribution. It's really cool. I'm going to give an example in a second. So this algorithm actually was invented many, many years ago, celebrating 50 this year. It's the Charlu algorithm. It was actually invented in a slightly different context, in the context of data compression. But later on, people rediscovered it in the context of BaseNet. People invented it a few more times. But really, a very nice algorithm that allows us to learn the most likely Bayesian tree. So let's give an example. And I want to finish with this and one comment. So what I'm doing here is I'm taking the 3 data points that we started with, 4 variables, and I'm running the algorithm on it. I'm cheating a little bit. You'll see in a second where. So first of all, we need to compute the parameters. So I have to compute P of A, P of B, P of C, P of D, which I computed there. Check. And then I have to compute all the pairs, P of AB, AC, AD, and so on, which I computed in the red column on the left, all the pairs. Now, notice that for each one, I have 4 numbers. Why do I have 4 numbers? Because P of AB can be 0, 0, 0, 1, 1, 0, 1, 1. And these are the 4 numbers that I have here. OK? So each pair here really is 4 numbers because I have 2 variables. And then I'm computing here the ratio, P of AB divided by P of A, P of B, for all the cases, because I need this for the mutual information. And then I'm computing the mutual information, right? Which, remember, is the sum over all xi, P of x, y, times the log of the ratio. Now, what I'm cheating here is that I didn't compute the log, because this will give us fractions and it will be ugly. So I just left it as if it's the ratio without the log of the ratio. It's still OK. We'll give you the idea. So that's what I got. So I'm assuming now that these are the mutual informations. And now I generate a tree. So I have a tree with 4 nodes. I start with a complete graph of all nodes. And now I'm going to generate a tree. So I'm going to run the spanning tree algorithm on it. So the first thing I'm going to choose is the heaviest edge. The heaviest edge here, OK, that's the formula for IXY, and I just didn't do the log. So this is the first one that I chose. I chose AB because I of AB is the largest here. There are a few ties here, but it's the largest, so I chose AB. Next one, I'm going to choose AD because it's also large here. The next largest is BD. I'm not going to choose it, even though it's the next largest, because if I choose BD, it's not going to be a tree, right? There's going to be a loop. So I'm skipping BD, and I'm going to the next largest, which is AC. So that's my spanning tree. OK? So I'm almost done with the algorithm. The next thing you have to do is you have to choose one of them, and this is your homework. You can choose B and compute the probability distribution. You can choose D and compute the probability distribution. And if you do a little bit of algebra, you'll convince yourself that it's the same thing. That's the problem. Okay, to summarize, we found a tree that maximizes the likelihood of the data. And in fact, it doesn't matter where we start. It finds the best tree that approximates the probability distribution that generated the data. So I'm not talking about how many examples you need to see so that you can actually approximate it well. It's the best approximation that you can get with the number of examples that we've seen. Okay, so I want to finish with one example, or going back to an example that we saw before. Really, the reason we do all this is because I got some data, just 3 examples here, and I really want to know what's happening for other examples. And it's important to realize that just the data is not going to tell me it. I have to make assumptions. So we need to assume a structure or a family of structures in order to do it. And this is really one of the key lessons that I want you to take from this. If you remember, a few months ago, we started with the badge problems. I gave you one sheet of paper with a lot of examples. And the question was, can we generalize from it? Can you get something that will predict whether any of your names is positive or negative? And just the data itself didn't tell you anything about your name. You had to make assumptions on what kind of functions you want to learn. Once you made these assumptions, you can take this data, find the best function of this type, and now you can evaluate it on any point that you want. What we've done today is exactly the same thing. We started with data. We cannot use it to make any predictions unless we say, okay, here is a family of functions that we assume, in this case, family of distributions. Let's take the data and find the best member in this family of distributions. Once we have this, we can make predictions. So really the same game that we've been playing from the beginning of the semester. We are done here. Questions? Okay, so I guess I'll see most of you on Monday for the poster sessions. If you don't want to come, I'll see you in the final. Thanks. No, we have a poster session. Hi.
Are you going to cover clustering?
No. No. Yeah. Yeah, we somehow ran slower this semester, so I didn't get to it. Yeah.
Were there lectures, videos for last semester?
Yes. Yeah. It should be on last semester's website.
Oh, okay.
Yeah. Yeah. It's there.
save screen. Perfect.